Hello, hello. So, good day. I am going to discuss with you now that we have got vectors out of the way, kinematics. Okay, so kinematics is a branch of physics that deals with the definition of motion of things. Okay, so it is under mechanics. Okay, so mechanics is basically the physics of motion. Okay, so kinematics is the mathematical way of defining what that motion is. Okay, so of course we have kinematics on all axes and both linear and circular motion. But today we're going to focus on just the x-axis, okay? And just linear motion. So here, like what I have said earlier. So if there's a frame of reference, that would be dynamics, okay? So we can see kinematics in all forms of motion. Well, it is very intertwined with our daily lives. So there, all right? Okay, so first we're going to determine the designation of variables. So I'm going to switch now to Microsoft Whiteboard to define all this. And then after this, we're going to proceed with the self-paced practice. The guided practice problems. Okay, so I'm gonna get this out of the way first before diving with that. So our first variable is change of displacement. So let's say this is u. Okay. And you're going to, let's say, the vaccination site. Okay. So to make it thematic. All right. So starting from that position, which is, of course, we don't know, you're going to go to the vaccination site. Okay. So let's say this is the vaccination site. There. So just don't mind the drawing. It doesn't matter. Okay. Let's just have a trapezoid instead. All right. So starting from this point, let's say point A to point B, you covered a certain distance. So we're going to call that distance, of course, from your starting point, x sub 0. Okay, and then the final point where you will be x. Okay, of course, operating on that. So you have final position minus initial position. Okay, so this is position, right? So there's a change in position. So this is delta x. So delta is a Greek word, a Greek letter, and we use it to define change. Okay? So this is the mathematical way of defining displacement. Okay? So ang unit na ginagamit natin is in meters. Next we have, according to the PowerPoint, we have time. Okay? So let's say you cover this distance with a certain time, let's say 60 seconds. Okay? So you started from 0 second and then you ended at 60 seconds. Okay? So those two definitions will be your t, okay, the final time, and of course, your initial time, which is t sub 0. So it is defined as, of course, delta t. Okay, there are times that, almost always on all are given, t is equal to 0, which means t minus 0 is equal to delta t. So it's fine if you either use final time or change in time. It's always gonna be the same. Okay, our unit for this in seconds. Okay, so this is time. All right. So what's next? Next, we have the first definition of motion, which is velocity. Okay, so dividing displacement by time, you will get velocity. Okay, so this is velocity. Its counterpart in scalar is speed. Okay, so you're going to see on certain occasions whenever we're solving a problem that velocity and speed are interchangeable. Okay, it doesn't matter. All right, so for now, if it is mentioned that you have to look for the direction, it's okay. If not, it's okay as well. Okay, either way, we're going to use velocity and speed interchangeably, although by definition, speed is scalar and velocity is vector. Okay, so the unit for this is meters per second. This is the SI unit, okay? Then of course, we have the second definition of motion, which is acceleration. So this is the rate of change in velocity. Let's say, from this point to this point, you were just walking, okay? And then you immediately saw that there are a bunch of people, okay, in the vaccination site. And of course, you want to grab your, what do you call this? Your slot as well. So from this point, going to this point, you started to run. So there's a change in velocity, right? So for us to determine that change, you're going to find, you're going to use acceleration. So acceleration is the rate of change in velocity defined by the change in velocity divided by the change in time. Okay, so this is acceleration. Our unit for this, so you take the unit of this, meters per second, okay, divided by the unit of this, okay, divided by seconds. Or of course, in a more familiar sense, meter per second squared. Okay, so we have, now that we have covered that, let us proceed on writing the kinematic equation. So together with those two, so we have the definition of velocity or definition of speed. Okay, I'll just show the part. Okay, so here we have defined those two. Now we can now jump into discussing, or showing the equations, and then how we are going to utilize them in problems. Okay, so you have first equation, V is equal to V sub 0 plus A delta T. Okay, so of course, this is final velocity. Okay, then this is initial. So reverting it back to the form of equation. So this is originating from the definition of acceleration. Acceleration wherein V minus V sub 0 is equal to A delta T. Okay, then V minus V sub 0 is of course delta V is equal to A delta T. Okay, divide both sides by delta T. Then you can cancel this. Okay, so basically, we just redefined acceleration. Okay, expressing it in form like this. Okay, expressing it in terms of its final velocity. All right, so this is our first. Okay, so for the second one, we have delta x is equal to v plus v sub 0 over 2 multiplied by delta t. So this is not very used often, okay, but we're going to include this anyway. So these are the instances wherein we are tasked to look for the average velocity. Okay, so average velocity is written like this. Okay, so it's usually, of course, the average of two velocities. If it is stated in the problem that what has been given is an average velocity, so by average is of course adding the number of course you have variables, so v sub 0 plus v sub 1 plus v sub 2 plus dot v sub n divided by n. Right? So in this case, it's sticking to 2. So I'm going to show a problem later that tackles the use of this. Okay, very seldomly used, but I'm gonna show you an example later. Okay, so as for the third kinematic equation, we have a delta t squared plus v sub 0 delta t. Okay, so delta x, which is the definition of this displacement. Okay, so I also refer to this as an equation that utilizes perfect square trinomial. Okay, or a quadratic equation to be more exact. So as you can see, our x is defined by delta t. Okay, diba in our what do you call this, standard form? So you have ax squared plus bx is equal to c, something like that. Okay, so if you rewrite it as like this, plus c is equal to 0, so that's the general form of a quadratic equation. Okay, so let's leave it like this. Then finally, our fourth equation, we have this. Okay, although either way of writing it is fine. So some write it like this: v squared is equal to v sub 0 squared plus 2a delta x. Okay, or you can find the square root, so that will be v is equal to v sub 0 squared plus 2a delta x square root. Okay, so either works fine. As you're going to see here, this is what we call the time independent equation. Okay, as time is not necessary for you to find the answer. Okay, so to sum it up, I'm going to write a table. So I'm going to box this one. Okay, although either works. Okay, so these are, including the previous two, are the kinematic equations. Okay, so to sum it up, the equations, you can write a table. So I'm going to do that. So I'm going to name this first, second, third, and fourth. So you can just go back to it. I don't want to rewrite the equations later. Okay? There. So I'm going to construct a table for you to easily determine when to use when. Okay, so we have the variables displacement, then we have time, we have velocity, then we have acceleration. Oops. It's okay if it's not aligned. The important thing is this is just a checkbox. Okay. So for the first equation, let's go back. Okay. So you could see what I am aiming to do. So we're going to check all the variables that is present on the equation. So we have v sub 0, a, and t. Okay. Actually, let's divvy this up, okay, into initial and final velocity. Instead of delta v, we have v and v sub 0, because usually those are the things that you look for. Okay, so we have v, then v sub 0 for initial velocity, then you have v. Okay, so for our first equation, we have, let's check again, v sub 0, a, and t. Okay, so we're going to check this, v sub 0, a, and t. It means if you're going to utilize the first equation, make sure that your given has no delta x or no displacement, no variable for displacement. Okay, so for our second equation, usually it looks like this. Okay, so you have delta x, v sub 0, and delta t. Okay, so you have delta x, v sub 0, and delta t. So in using the second equation, there should be no acceleration on your given. Okay, what does that mean? So this should comprise given plus required. Okay, it means when you're writing the variables of the given and the required, the one that has an X mark here should not be present on your given required. I'll elaborate it further when we're going to have our guided examples. So for our third equation, we have delta x. Okay, so we have delta x, or let me rewrite this one. So we have delta x, we have a, we have t, so delta t squared tsaka t, then we have v sub 0. So in this case, the final velocity is not given, okay, or the final velocity cannot be found on the word problem. And then lastly, we have the fourth equation, wherein, as I have said earlier, it has no time because it is a time independent equation. So just check everything else. Okay, so sir, how are we going to use the table? Okay, so this will be very handy when you're doing the problem solving, which I will be showing now. Okay, so let's go back here. Okay, so here's our first problem. So a racehorse coming out of the gate accelerates from rest to velocity of 15 meters per second due west in 1.8 seconds. What is its average acceleration? So let's write our given. So first we have initial velocity. Okay, so sir, where's our initial velocity there? It is here, v sub 0. Okay, so you accelerate from rest. So starting from rest, you have a change in velocity. That's why it's acceleration, right? Because it is a change in velocity. Okay, so our final velocity, which is v, is equal to 15 meters per second. Okay, so the direction doesn't matter, it's fine. Okay, So we can just rewrite it on the final answer. For our time, it is 1.8 seconds. All right. And then for our required, we have acceleration. So as you can see, this is what I'm referring to. Upon writing your problem, you should be able to see these variables. Okay. So you line them up very nicely so you can see, and then cross check it with the table. So let's check. So you have v sub 0, v, delta t, and a. So going back to our table, we have v sub 0, delta t, and a, which means we're going to use the first equation. Okay? You got that? Check again. There. So you have v sub 0, delta t, and a. So for your equation, you're going to use the first one. So I'm going to write it. So you have v is equal to v sub 0 plus a delta t. So you can check, right? So you have v sub 0, you have a, and then you have delta t. So it checks out. All right? And then the next thing, it's up to you at this point. So for me, I prefer rearranging the variables first so that all of the given will be on one side and then the required will be on the other side. So in this case, we're looking for acceleration. So we want acceleration to remain as a single variable on, in this case, the right-hand side of the equation. So first thing, this is separated by addition. So transpose v sub 0 to the other side. V minus v sub 0 is equal to a delta t. Okay. Then of course, since what we need is a, we divide both sides by delta t. So in this case, you're going to cancel out delta t, leaving you with the equation that you want. Of course, the one that will be helping you to solve this problem. So you have v minus v sub 0 divided by delta t. So in this case, you can now proceed on the solution. You can just continue. So substitute. So you have 15 meters per second minus 0 divided by what's our delta t? 1.80 seconds. There. So how about we open a calculator so we could show the answer. So we have 15 divided by 1.8. There. So our answer is 8.33. Acceleration is equal to 8.33. You check the units, meters per second divided by second. So that's meter per second squared. So it checks out. So you can now box this because that's our final answer. Okay, so let's proceed on the second problem. So in steadily increasing your velocity from 30 kilometers per hour to 60 kilometers per hour in 30 minutes, how much distance can you cover? Okay, so for our given, we have initial velocity, which is v sub 0. So this is a tip, very useful tip. Generally, or almost all of the time, you check then as well if it fits on the situation. When your v sub 0 is not 0, most probably you're going to use the second kinematic equation. Okay, so kilometers per hour. Then we have final velocity, which is 60 kilometers per hour. Okay, our time is delta t, 30 minutes. Okay, and then finally our required is distance or displacement. So in this case, delta x. Right? So taking a look at our table. So what's the variable that is missing? It is a, right? So taking a look here at our table. So let's just proceed on writing the equation. So we have delta x is equal to v plus v sub 0 divided by 2 multiplied by time. Okay? So as you can see, the units are not similar. So you can convert them. Okay? So in this case, I'm going to convert. So we can now proceed on our solution. Okay, so you have delta x. Well, it's already written properly because our required is delta x, right? So our delta x is gonna be, this is 3. Okay, so you have 8.333 meters per second plus 16.6667 meters per second. Okay, then we divide this by 2. Multiplied by time, which is 1,800 seconds. Okay, so you can now input that on your cycle. Let's see, or let's check the answer. Okay, so we place a parenthesis here and here, divide by 2. Then we're gonna place another parenthesis here and here, so we could multiply them. So our time is 1800. Okay. So there, meters. Okay. So as you can see, if you add this, you're going to cancel this. All right. So there you go. Okay, so compare it to your required. So your required is delta x. Okay. So let us proceed now on our third problem. So Ferrari LaFerrari, blah, 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 blah. Our acceleration is 26 meters per second squared. That's very fast. Okay. So it can accelerate from a speed. So it means our initial velocity has a value. Okay, take a look at our grammar here. Suppose such a race car accelerates from a speed of, okay, so it means it's going to start at that certain speed. Okay, so this is 20 meters per second. All right, and then our time is 5.56 seconds. There. So what we want to find out is how far. So that's again displacement. Okay. So take a look at our table. So we have A, V sub 0, delta T, and delta X. Okay. So where's our table? So we have A, V sub 0, delta T, and delta X. So in this case, V, or final velocity, is not included in our problem. So it means the equation we're going to use is the third equation. Oops. There. Okay. So our equation is delta X is equal to A delta T squared over 2 plus V sub 0 delta T. Okay, so for our solution, this is already written as it is, so you can just substitute. So you have delta X is equal to, what's our A? 26 meters per second squared multiplied by time, 5.56 seconds. This is squared, okay, divide by 2. Then plus V sub 0 is 20 meters per second. Then finally time, 5.56 seconds. So before we input this in our cycle, we show the cancellation of units first. So if you square this, I'm going to distribute the square, okay? So this is cancelled. Okay, so because this is second squared, divide by second squared, right? And then this is meter per second multiplied by seconds. So seconds divided by seconds. So cancel this as well. So you're left with meters as a unit. So since this is addition, you're just going to copy the variable or the unit, which is in this case is meters. Okay, so let's proceed on solving this. So we have 26 multiplied by 5.56 to be squared. Okay, then we divide this by 2. There. Then we have addition. Okay, so this is 20 times 5.56. There. I'm going to so there's our answer. Okay, so our answer is 518.88. Our unit is of course in meters. So there. All right, and then finally we have this one. So this will be our last problem. Okay. So let's take a look at our given. So the car starts from rest according here. Okay, so we have V sub 0 is equal to 0. And then it ended at a speed of 20 meters per second. Okay. And then it reached a displacement of 120 meters. Okay. So you have delta x is equal to 120 meters. So for our record, we're looking for acceleration. So if you're paying attention, the final equation, of course, will be, the equation that we're going to use is the equation that is not yet used, which is the time independent equation. So you have v squared is equal to v sub 0 squared plus 2a delta x. Okay, so in this case, we're looking for a, or for acceleration, so we're going to rewrite the equation. Okay, so first is to transpose the initial velocity to the other side, leaving 2a delta x on one side. Okay, and then since what we want is just a, so we want a to remain on the right hand side of the equation. So we're going to divide 2 and then delta x. Then we do it on the other side as well. So in this case, you can cancel out 2 and then you can cancel out delta x. So you're left with a. Okay, so you have a is equal to v squared minus v sub 0 squared divided by 2 delta x. For your solution, just substitute. So you have a is equal to, what's our v? 20 meters per second to be squared. Minus, so that's 0. Divide by 2 times 120 meters. There. So let's proceed on answering that. So you have okay, so our acceleration, or our final answer, is acceleration of 1.67. Our unit is, or let's show the cancellation, the cancellation. So you have 20 squared, then you have meter squared and second squared. Okay, so I distributed the operation. Okay, so here you're going to cancel 1 meter to divide on your denominator, because if you write the units, it's gonna be meter times meter divided by second times second divided by 1 over, or divided by meters, like that. So right, exact like this, right? So rewriting it will gonna be meter multiplied by meter. Then I'm just gonna write the second squared multiplied by 1 over meters. So rewriting this, you look for the reciprocal. Okay, so as you can see, you can cancel this. So you're left with the unit of meters per second squared, which is of course the unit for acceleration, the one that we want. Okay, so now you can proceed on practicing yourselves by answering the self-paced practice problems. Okay, and then your teachers will be preparing some more examples for you to practice with. Okay, so thank you and may you all have a good day.